So this is part one of how to do moving geometry. So what we're going to do is just a 2D example. And we are going to use mass transfer of dilute species. Click plus. Adding. Computer's being slow. And we are going to use deformed mesh, deformed geometry. Click plus. Click next. And we're going to look at time dependent. Okay, so this is meant to be a very basic example. And what we're going to look at is a square. We're going to make a point one, build all. Okay, so there's our square. Okay, so for our transport of dilute species, we're not going to do anything special. We are just going to say that the diffusivity is 1e negative 6. The initial value in the domain is 10. We are going to leave no flux on the boundary. And we're going to have no convection. And we're going to do deformed geometry. You can leave all this as is. So for the deformed geometry, we're going to shrink our square in half. And so what we need to say is the square can freely deform, and then we need to give one of the boundaries to move. So we're going to say this top boundary shrinks at a rate of negative 0.005 meters per second squared. And we're going to run this for 10 seconds, and so this square should be cut in half. One more thing before we go run this now is we need to prescribe the mesh displacement on these two sides to say that x does not change and y can do whatever. So basically this top is going to come down and the sides are going to shrink with it. If we said the y is 0, what's going to happen is it's going to become a parabola. Okay. So we're just going to record every second for 10 seconds. And so what we should see is I have a concentration of 10 here, and it's going to be cut in half, and so I should see a surface plot of 20 at the end. So, and for mesh, I'm just going to do, say, free triangular, size, just do extra fine. That's reasonably okay. And I'm just going to click run, and I'm going to stop this and be back in a second. Okay, so I'm back now, and what I see is that my concentration did not double, which is not good. So at 0, it's 10, and at 10 seconds, it's still 10. Okay, so what happened was the mesh moved, but the concentration of species did not move. And what happens is there's actually a convective flux relative to the geometry. And so this transport of dilute species, we actually need convection, and you're actually going to need it to be in the conservative form. So the conservative form, non-conservative form, if you look at the equation without it and with it, so it's the velocity is non-compressible. So we're assuming it's compressible. Okay. So, but we still need a velocity. Well, it's not moving in the x direction, it's only moving in the y. Well, what's the y velocity? It's the velocity of the mesh. And that variable is time. So this could also be written dy time. And if you want to see where I got that from, you can come down to equation view under deformed geometry. We can come all the way down here. And we can see the mesh velocity in the y direction is dy time. But for lazy way of writing it, you could just write y time. Okay, so now we should be good. So I'm going to solve this once again, and it should work this time. Okay, so I just ran it once again, and I look at the concentration in 10 seconds, And it looks great. I got 20 everywhere. Oh, I just assume I have this error at the boundary at the top here. Well, that's actually not an error. That's actually, you need to specify a boundary condition for the transport of dilute species such that drug isn't leaving the boundary. So there's actually a flux at that top boundary. So we're going to redo this one more time. So what that boundary actually is negative c times y time. So what that says, it's the convective flux. So there's a diffusive plus convective flux. Well, there's no diffusion going out. And so what we have is the concentration there times y time, and we need to have the correct direction, so we need a negative. So we're going to rerun this one more time, and hopefully it should look a lot better. Okay, so we're back. It ran. It looks kind of but what you see is the legend is it's approximately 20, which is what we hope. Now if we zoom in here, this is why you do a mesh convergence, because you don't want all these like little squiggly lines, and that can be fixed by refining your mesh, or one solution could be change your discretization from linear to quadratic. So the space in between elements and how it's approximated. Okay, but this is part one of how to do a deformed geometry, and I will do 2 more parts, and I will be back in a second.